There's a smallest distance in nature where our equations fall silent, a boundary so fine that space itself no longer behaves like space, and time no longer flows the way we expect. At that scale, the universe does not reveal more detail. It gently refuses to answer. Physics, precise and powerful everywhere else, begins to loosen its grip. If this quiet journey brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or simply your presence helps keep these calm explorations alive more than you know. Now, we drift inward toward the first truth. Part 1. Where measurement stops meaning anything. If you could keep zooming in forever, past molecules, past atoms, past even the smallest particles we know, would reality continue to sharpen, or would it begin to blur? At the edge of physics, measurement itself loses meaning, not because our tools are weak, but because the universe no longer allows sharp edges to exist. For most of human history, we assumed that the universe was built like a finely crafted machine. If something looked smooth, it was only because we hadn't looked closely enough yet. Stone became grains of sand, water became droplets, flesh became cells, and cells, once invisible, became familiar shapes under glass lenses. Each improvement in magnification revealed another hidden layer, another quiet structure waiting patiently beneath the surface. This success trained us to believe that reality was infinitely divisible, that no matter how small we went, there would always be something there to see. Physics encouraged this belief for a long time. Atoms, once thought indivisible, were found to contain electrons circling a dense nucleus. That nucleus, in turn, revealed protons and neutrons, and those, when struck with enough energy, revealed quarks, smaller components bound together by forces that only reveal themselves under extreme conditions. Each discovery came with a sense of calm triumph. The universe, it seemed, was willing to show its inner workings layer by layer, as long as we asked with enough precision. But precision has a cost. To see smaller things, physics demands higher energy. This is not a limitation of engineering, it is a law of nature. Waves can only resolve details larger than their own wavelength. Light with long wavelengths reveals large structures. To see smaller structures, the wavelength must shrink, and shrinking wavelength means increasing energy. At first, this trade-off feels manageable. Visible light gives way to ultraviolet. Ultraviolet gives way to X-rays. X-rays give way to particle beams. Electrons accelerated to immense speeds begin to behave like waves, fine enough to map the shapes of atoms themselves. And for a while, this works beautifully. But as you continue this journey inward, something subtle begins to change. Energy does not merely illuminate, energy gravitates. This is a quiet truth of the universe. According to the Aichi-Tineido relationship described by Einstein, energy and mass are interchangeable. Concentrate enough energy into a small enough region, and space-time itself responds. It curves, it bends, it resists. At everyday scales, this effect is invisible. A flashlight does not warp the room. A microscope does not bend the table beneath it. But as energies climb higher and regions shrink smaller, gravity can no longer be ignored. Eventually, the act of observation begins to interfere with the stage on which the observation takes place. This is where measurement starts to lose its footing. As you push toward ever smaller distances, the energy required to probe those distances becomes so intense that it distorts space-time itself. The region you are trying to examine no longer sits calmly beneath your instruments. It begins to curve inward, pulled by the weight of your own attempt to see it. If you persist, if you continue to compress more energy into a smaller region, the equations predict something remarkable and unsettling. The region collapses behind a boundary from which no information can escape. A microscopic horizon forms, not metaphorically, physically. At that point, measurement does not fail because your tools are imprecise. It fails because the universe has closed the window. Beyond this boundary, concepts like distance and location lose clarity. You can no longer say where something is because the geometry of space itself has become unstable. The very notion of here dissolves. This is not a technological problem waiting for a clever solution. It is a structural feature of reality. Physicists refer to this boundary as a fundamental limit, a scale where our familiar ideas about space, time, and measurement no longer apply. Below it, the smooth fabric we experience as space is no longer smooth. It flickers, it fluctuates, it becomes uncertain. Imagine standing at the shore of a calm lake. From a distance, the surface appears perfectly still. As you step closer, you notice gentle ripples. Closer still, tiny waves overlap and interfere. And if you could somehow observe the water molecule by molecule, the idea of a single flat surface would disappear entirely. The Planck scale is like that final step, but for space-time itself. At this scale, space is no longer a quiet backdrop. It becomes active, dynamic, restless. The geometry you rely on to define distance and direction refuses to stay fixed long enough to be measured. Time, too, begins to loosen its grip. Events no longer unfold in a clean sequence. Cause and effect blur. The idea of a precise moment becomes as unstable as the idea of a precise location. And this is where a profound shift occurs in how physics understands reality. For centuries, measurement was seen as a passive act. You look, you record. The universe continues unchanged. But near this boundary, measurement becomes participatory. The act of observing changes the thing observed, not slightly, but fundamentally. To ask a question too sharply is to erase the answer. This is why physicists say that below a certain scale, asking how small stops making sense. Not because the universe is hiding something maliciously, but because the language of measurement itself breaks down. Length is no longer well-defined. Time is no longer continuous. Even the idea of a point in space becomes ambiguous. In this regime, the equations we trust begin to contradict each other. Quantum mechanics insists that uncertainty is unavoidable. General relativity insists that energy shapes geometry. Both are correct. And together, they create a region where certainty itself cannot exist. This realization is not loud or dramatic. It arrives gently, like a dimming light. The universe does not explode into chaos at small scales. It simply refuses to be pinned down. And there's something deeply calming about that. Because this limit tells us that reality is not infinitely sharp. It has a texture, a grain, a softness that prevents it from collapsing into infinities and paradoxes. Without this boundary, the equations predict absurdities. Infinite densities, infinite energies, infinite information packed into zero volume. The universe avoids these extremes not through complexity, but through restraint. It draws a quiet line and says, this far and no further. In doing so, it preserves stability. Stars can form, atoms can exist, time can flow in a way that allows memory, motion, and life. So when we say that measurement stops meaning anything at this scale, we do not mean that knowledge ends. We mean that knowledge must change form. Beyond this point, reality may still exist, but not in ways that rulers, clocks, or coordinates can describe. Whatever lies beneath is not arranged in neat distances and durations. It is something deeper, something that does not submit to being sliced thinner and thinner. As you rest here, breathing slowly, consider this quiet truth. The universe is not a machine made of infinitely precise parts. It is a structure with limits, limits that protect coherence, prevent collapse, and allow complexity to emerge. And as we continue this gentle journey inward, one question naturally follows. If space and time themselves lose meaning at this boundary, what then are they made of? Part 2. The scale. No ruler can touch. There is a length so small that distance itself becomes uncertain. At this scale, asking how far no longer has a clear answer. Space stops behaving like a smooth surface and instead becomes restless, fluctuating beneath every attempt to define it. For most of your life, distance feels absolute. A room has corners, a road has length. Even the vastness of the night sky feels measurable, mapped in light years and angles. Distance feels like one of the most reliable features of reality, something that exists whether you observe it or not. You can close your eyes, and the space around you remains. Physics once believed this too. For centuries, space was treated as a silent stage, an invisible grid where events happened but which itself never changed. You could mark a point, draw a line, divide it in half, and divide it again, forever. In this view, distance had no smallest unit. It was infinitely divisible, like a mathematical line stretching without texture. But nature, it turns out, does not share our love of perfect lines. As physics advanced, scientists began to suspect that space might not be continuous after all. Just as matter is made of atoms, perhaps space itself has a smallest grain, a scale below which the idea of distance dissolves. This suspicion did not arise from philosophy, it emerged from equations. When quantum mechanics and gravity are pushed toward their limits, they both begin to whisper the same unsettling suggestion. There exists a minimum meaningful length, not because smaller lengths do not exist, but because they cannot exist in any measurable sense. Below this scale, space cannot be pinned down long enough to be defined. Imagine trying to draw a line on the surface of a stormy ocean. From far away, the water looks smooth. You might even believe you could measure a straight distance across it. But as you move closer, waves rise and fall. Any line you draw is immediately distorted, erased, rewritten. The surface refuses to hold still. At extremely small scales, space behaves in a similar way. Quantum theory tells us that uncertainty is fundamental. You cannot know both the position and motion of something with perfect accuracy. The more precisely you try to locate an object, the more violently its momentum fluctuates. At large scales, this uncertainty is negligible. At small scales, it becomes dominant. Gravity adds another layer. Energy bends space, and measuring smaller distances requires higher energy. When you try to confine that energy into an ever smaller region, space itself reacts. It curves, twists, and resists being compressed further. Eventually, these two effects collide. Quantum uncertainty demands fluctuations. Gravity demands curvature. Together, they turn space into something unstable, something that cannot remain fixed long enough to be measured cleanly. At this boundary, the idea of a ruler becomes meaningless. A ruler assumes that space is stable between its markings, that the distance between 2 points remains the same while you measure it. But at this scale, space itself is in constant motion. It stretches and contracts, not smoothly but erratically, as if reality itself is breathing. You could place a ruler here, but the space beneath it would change before you could read the result. Distance stops being a property of the universe and becomes an approximation, a statistical average over something far more restless. Physicists sometimes describe this regime as spacetime foam, not because space literally bubbles like soap, but because its geometry fluctuates on incredibly small scales. Tiny curvatures form and vanish, connections twist and reconnect. The familiar idea of a flat, continuous expanse gives way to something granular and alive. In this environment, the question, how far apart are these 2 points, has no single answer. The distance changes depending on when and how you ask. This is deeply counterintuitive because distance feels like one of the most objective features of existence. But at this scale, objectivity itself softens. Even the concept of a point becomes unstable. A point in geometry has no size. It exists at an exact location. But in quantum physics, there is no such thing as an exact location. Every attempt to define a point spreads it out into a probability cloud. And when gravity joins the picture, that cloud gains weight. It bends the space it occupies. So the point distorts the stage it stands on. The universe refuses to let anything be infinitely precise. This refusal is not an inconvenience. It is a safeguard. Without a minimum scale, physics predicts impossible extremes, infinite energy densities, singularities that break every equation, a universe that collapses under the weight of its own infinities. The smallest length acts like a pressure valve, preventing reality from tearing itself apart. It tells us that nature values consistency over sharpness. You might imagine that below this scale, space simply stops existing. But that is not quite right. Something is there, something deeper than distance as we understand it, but it does not arrange itself into neat coordinates or measurable intervals. It may be relational rather than spatial, a network of connections rather than points, a structure defined by interactions instead of distances. We do not yet know. What we do know is that this scale marks the end of familiar geometry. Angles lose meaning. Straight lines curve unpredictably. Parallel paths may meet and separate again. Even time becomes entangled with this uncertainty. Distance and time are woven together. When space fluctuates, so does duration. The idea of how long becomes just as unstable as how far. Moments blur, sequence phrase. The universe no longer provides a clean timeline for events to unfold, and yet, this chaos does not leak upward into your everyday life. At the scales you inhabit, space averages out, fluctuations cancel, geometry becomes smooth again, distances stabilize, the world regains its familiar structure. This is why you can walk across a room without falling into quantum uncertainty, why planets maintain their orbits, why light travels predictable paths across the cosmos. The restless behavior of space is confined to scales so small that they never intrude directly into experience, and there is something profoundly comforting in that. It means that the universe has layers, that beneath the calm surface, deeper processes unfold without disturbing the harmony above. The same way atoms vibrate without shaking mountains. The same way cells divide without tearing the body apart. As you lie here, breathing slowly, imagine that beneath everything solid and stable, space itself hums quietly, not loudly, not violently, just enough to prevent perfection, just enough to allow structure without rigidity. The smallest length is not a wall you crash into. It is a horizon, a soft boundary where questions change shape instead of stopping outright. Rulers fail here not because knowledge ends, but because knowledge must let go of certainty. And as we continue this inward journey, one question gently waits for us ahead. If space cannot be measured cleanly at this scale, what happens when energy keeps increasing anyway? Part 3. When energy becomes gravity. To see smaller things, physics demands more energy. But energy has weight. As it concentrates into tinier regions, it begins to curve space around it. Eventually, the act of looking creates gravity strong enough to hide what you are trying to see. At first, this idea feels almost poetic rather than real. We are used to thinking of gravity as something large and obvious. Planets pulling on moons, stars binding galaxies, massive objects shaping the paths of light across the cosmos. Energy, by contrast, feels abstract, invisible, something that flows, not something that presses down. But the universe does not make this distinction. In the language of physics, energy and mass are deeply intertwined. They are not separate substances, but different expressions of the same underlying quantity. This means that anything carrying energy, no matter how intangible it seems, contributes to gravity. Light gravitates, heat gravitates, even the energy stored in empty space plays a role. Most of the time, this effect is vanishingly small. A beam of light passing through a room does not noticeably bend the walls. A particle accelerator does not collapse the building around it. At everyday scales, gravity from energy is drowned out by the mass of matter itself. But as you push deeper into the microscopic world, the balance shifts. To resolve smaller distances, you must use shorter wavelengths. Shorter wavelengths mean higher frequencies. Higher frequencies mean more energy packed into a smaller region. Each step inward requires a sharper, more intense probe. And with each step, the energy density rises. Eventually, energy stops behaving like a gentle messenger and begins to act like a sculptor. According to the principles laid out by general relativity, energy tells space how to curve. This is not metaphor, it is geometry. The presence of energy changes the shape of spacetime itself, altering what paths are possible and which are forbidden. At modest energies, this curvature is gentle. Light bends slightly around stars. Time ticks a bit slower near massive objects. These effects are measurable but subtle. But as energy is forced into ever smaller regions, curvature intensifies. Imagine pressing your finger into a stretched sheet. A light touch creates a shallow dip. Press harder and the fabric bends deeply. press hard enough in a small enough area, and the sheet tears or folds into itself. Spacetime behaves in a similar way. When energy becomes concentrated beyond a certain threshold, space curves inward so strongly that it forms a boundary, a surface beyond which paths no longer lead outward. Information cannot escape. Even light, the fastest thing in the universe, finds no route back. This boundary is not an object. It is a consequence. It arises naturally from the equations, whether we like it or not. What makes this especially unsettling is that this boundary can be created not by stars or collapsing planets, but by the act of measurement itself. When you attempt to probe extremely small distances, you inject enormous energy into a tiny region. And if that energy density becomes high enough, the region you are trying to observe disappears behind its own gravity. Your question creates its own silence. This is the moment where physics turns inward and gently stops you, not with a warning, not with an explosion, but with a horizon. At this point, asking what is inside no longer has an operational meaning. You cannot retrieve information from beyond the boundary. No signal can carry it back. The universe has, in effect, drawn a curtain. This is not because it is hiding something maliciously. It is because the laws that allow information to travel have been overwhelmed by the geometry created by your attempt to look. Energy has become gravity. This realization marks a profound shift in how we understand limits in physics. In most sciences, limits are practical. Better tools, better methods, better patience might overcome them. But this limit is fundamental. No clever engineering can bypass it because the barrier arises from the very act of probing. If you try to reduce the energy to avoid gravitational collapse, your probe becomes too coarse to see the structure you are interested in. If you increase the energy to sharpen your view, gravity intervenes and hides the region entirely. There is no middle path. This balance creates a natural boundary, a smallest meaningful length and a smallest meaningful time. Below these scales, the universe refuses to cooperate with our definitions. And yet, this refusal is not chaotic. It is orderly in its own way. The equations that predict this behavior are consistent, precise, and deeply elegant. They tell us that reality is not infinitely compressible, that information density has a limit, that the universe values coherence over infinite detail. Without this behavior, the cosmos would be unstable. Tiny fluctuations could collapse into catastrophic singularities. The structure of space-time itself would be riddled with infinities, making prediction impossible. Instead, gravity steps in as a regulator. It smooths the extremes. It prevents runaway compression. It ensures that energy cannot be packed arbitrarily tightly without consequence. This makes gravity not just a force, but a guardian of consistency. At human scales, gravity feels heavy and slow. At cosmic scales, it shapes galaxies and clusters, and at the smallest scales, it becomes the quiet enforcer of limits, stepping in when quantum curiosity pushes too far. It is remarkable to consider that gravity, the weakest of the fundamental interactions in everyday life, becomes dominant precisely where everything else breaks down. At extreme energies, its influence grows until it overrides all other forces. This inversion is one of the great ironies of physics. The closer you look, the heavier reality becomes. And in this heaviness, geometry itself takes command. Distance contracts, time stretches, paths curve inward. The freedom to observe collapses into inevitability. This does not mean that knowledge ends here. It means that knowledge changes character. Instead of asking what exists at smaller and smaller scales, physics begins to ask different questions. What patterns are allowed? What relationships remain invariant? What structures emerge when space and time are no longer fundamental? These questions are quieter, more abstract, but they are no less profound. As you rest here, imagine this balance playing out beneath everything you know. Energy flowing, space responding, gravity quietly shaping what can and cannot be known. The universe is not brittle. It does not shatter when pressed. It bends, it curves, and when pushed beyond its tolerance, it closes gently, protecting its deeper structure. And as we continue this calm descent toward the limits of understanding, another question naturally rises. If gravity can emerge from energy itself, what happens when space and time are no longer smooth enough to carry gravity at all? Part 4. The birth of the Planck Wall. At a specific threshold, the universe draws a quiet line. Beyond it, probing deeper no longer reveals structure, only collapse. This boundary is not technological, it is built into reality itself, a limit written into the fabric of space-time. For centuries, science advanced by assuming that every wall was temporary. When one method failed, another would eventually succeed. When an instrument reached its limit, a better one would be built. This pattern shaped our confidence. It taught us that the universe always had more to reveal, if only we were patient and precise enough. The Planck Wall is different. It does not stand in the way like a locked door. It does not challenge us to invent a stronger key. It simply marks the point where the questions we are asking no longer make sense in the language we are using. This boundary emerges from a convergence of ideas that, on their own, work flawlessly. Quantum mechanics governs the very small with extraordinary accuracy. General relativity governs gravity and space-time with equal precision. Each theory has been tested endlessly, confirmed in laboratories and across the cosmos. But when they are forced to operate together at extreme scales, something remarkable happens. They refuse to cooperate. As you push toward smaller distances, quantum mechanics demands higher energy. As energy increases, general relativity demands stronger curvature of spacetime. When both demands are satisfied simultaneously, the result is not clarity, but closure. This is the moment the Planck Wall is born. It is not a physical object. It has no surface you could touch. It is a threshold in behavior, a point at which the universe stops responding linearly to our attempts to examine it. Below this scale, adding more energy no longer reveals smaller structure. It simply deepens gravitational collapse. The universe does not fracture into finer details. It folds inward. In this sense, the Planck Wall is not something you crash into. It is something that forms because you are approaching. The closer you get, the more it solidifies. To understand why this happens, it helps to imagine what measurement really means. Every measurement is an interaction. To see something, you must exchange energy with it. Light reflects, particles scatter. Information is carried by physical processes. At everyday scales, this exchange is gentle. The object remains intact, the space around it remains unchanged. But near the Planck scale, the exchange becomes overwhelming. The energy required to resolve such tiny distances is so concentrated that it reshapes the very region being measured. Spacetime does not sit passively beneath the probe, it reacts. At a certain point, that reaction becomes irreversible. The region you are trying to examine collapses into itself, forming a boundary from which information cannot return. The probe does not fail. It succeeds too well. This is the essence of the Planck Wall. It is not imposed by ignorance, it is imposed by consistency. The universe enforces it to prevent contradiction. Without such a boundary, the equations predict absurd outcomes: infinite curvature, infinite energy density, physical quantities that lose all meaning. The Planck Wall prevents these infinities not by canceling them out, but by preventing the conditions that create them in the first place. It acts like a safety valve built into reality. This idea runs counter to our intuition. We are used to thinking that limits exist because we are limited, because we lack precision, because we lack power. But here, the limit exists because the universe itself refuses to define anything smaller. Below this threshold, the concepts of where and when dissolve. There is no fixed background in which events unfold. Space and time themselves fluctuate too violently to serve as coordinates. This is why physicists say that space-time becomes ill-defined at the Planck scale, not broken, not destroyed, simply undefined. Imagine trying to draw a map of a place that changes shape faster than you can observe it. Any line you draw is immediately outdated. Any coordinate you assign loses meaning before it can be used. The problem is not that the place does not exist, it is that mapping itself no longer. behaves predictably, allowing light to travel for billions of years without losing its way. This stability is so complete that we rarely question it. Space feels like the most reliable ingredient of reality. For a long time, physics agreed. Classical physics treated space as a fixed stage, an invisible framework that existed independently of whatever happened within it. Objects moved through space, forces acted across it, but space itself remained unchanged. It did not ripple, vibrate, or respond. It simply was. Even when Einstein revealed that space and time could bend under gravity, the bending was still smooth. Space-time curved like a gently stretched fabric. Geometry changed, but it did so continuously, predictably, and calmly. This picture works beautifully across almost everything we can observe. But when physics follows its own equations inward, toward the smallest scales imaginable, that calm geometry begins to dissolve. At extremely small distances, quantum mechanics insists that nothing stays still. Fields fluctuate, energies jitter, even empty space seethes with activity. Particles appear and vanish. Measurements refuse to settle into fixed values. At the same time, gravity insists that any energy present must shape space. Even fleeting fluctuations curve geometry, if only for an instant. And when those fluctuations become intense enough, their effects can no longer be ignored. Together, these principles transform space from a smooth backdrop into something far more dynamic. Near the Planck boundary, geometry itself becomes unstable. Instead of a flat surface or a gently curved one, space behaves more like a restless sea. Tiny regions swell and collapse. Connections stretch and snap back. Directions lose their permanence. What counts as near and far can change from one moment to the next. This does not happen in dramatic bursts. There are no explosions or flashes. The instability is subtle, constant, and incredibly fast. It unfolds at scales so small and time so brief that they average out at larger distances. That averaging is what you experience as smooth space. Much like the surface of water appears flat from a distance but reveals waves upon closer inspection, space appears calm because you inhabit a scale where its fluctuations cancel out. The ripples are too small and too rapid to disturb the larger pattern. But at the Planck scale, there's no distance large enough to smooth them away. Here, the concept of geometry itself begins to fail. Lines no longer remain straight long enough to be defined. Angles fluctuate. Areas and volumes lose stable meaning. Even topology, the basic idea of what is connected to what, can change moment to moment. Space becomes less like a container and more like a process. This challenges one of our deepest intuitions, that space exists independently of what fills it. At these scales, space may not be something things occupy, but something that emerges from their interactions. Instead of particles moving through space, space may arise from relationships between particles. Instead of geometry being fundamental, it may be a statistical description of deeper activity. In this view, smooth space is not basic, it is an approximation. What you experience as distance is the average behavior of countless microscopic fluctuations settling into a pattern that feels stable at large scales. Remove the averaging, and the pattern dissolves. This idea helps explain why attempts to define exact distances near the Planck scale fail so completely. You are trying to measure something that does not hold still long enough to be measured. The ruler assumes stability. Space does not provide it. It also explains why space-time appears continuous only when viewed from far enough away. Just as temperature is a meaningful concept only when averaging over many molecules, geometry may be meaningful only when averaging over countless microscopic configurations. At the deepest level, there may be no smooth surface at all, only activity. Physicists sometimes describe this activity as quantum foam, not because it looks like bubbles in any literal sense, but because it captures the idea of constant formation and dissolution. Tiny regions of curvature emerge and fade. Connections form and break. The geometry is never settled. In such an environment, the classical notion of a point loses meaning. A point assumes an exact location, but location itself fluctuates. Any attempt to pin it down spreads it out, blurs it, and alters the surrounding geometry. Space refuses to be sharply defined because sharpness itself is incompatible with its underlying behavior. This refusal is not arbitrary. It arises from the same principles that allow the universe to exist in a stable form. If space were perfectly smooth at all scales, quantum fluctuations could concentrate infinite energy into infinitesimal regions. Geometry would collapse into singularities everywhere. Reality would tear itself apart. By refusing smoothness at the smallest scales, space protects itself. The fluctuations prevent infinite compression. The instability diffuses extremes. The geometry never allows itself to become infinitely sharp or infinitely curved in one place. In this sense, roughness is a feature, not a flaw. It ensures that spacetime remains self-consistent, that cause and effect retain meaning at larger scales, that the universe does not collapse into pathological infinities. And importantly, this roughness remains hidden. You do not feel it beneath your feet. Light does not scatter randomly as it crosses space. Planets do not wobble unpredictably. The smoothing effect of scale restores order. This layered structure, chaos beneath calm, is one of the universe's most elegant strategies. It allows freedom at the smallest scales and stability at the largest. It permits unpredictability without destroying coherence. It balances restlessness and reliability. As you breathe now, consider how this mirrors other systems you know. Your body is alive with microscopic motion. Molecules vibrate, cells divide, electrical signals flicker through neurons, yet your experience is one of continuity. You remain yourself from one moment to the next. Space may work the same way. What feels like an unchanging stage may actually be a constantly renewing process, its deeper turbulence smoothed into serenity by scale. And this realization carries a quiet humility. It reminds us that the structures we rely on, distance, direction, geometry, are not absolute. They are emergent, useful, reliable, but not fundamental. At the Planck boundary, the universe is not broken. It is simply operating in a regime where our familiar concepts no longer apply. Smoothness is something space achieves, not something it possesses intrinsically. And as we continue this gentle descent into the foundations of reality, another question begins to surface. If space itself is restless at its core, what happens to time when geometry can no longer stay still? Part 6. Time begins to fray. Time so steady in daily life loses its rhythm here. Seconds no longer flow cleanly from one to the next. Cause and effect blur. The future and past become harder to separate, not philosophically, but physically. In ordinary life, time feels like the most reliable companion you have. It moves forward at a constant pace. One moment follows another. Clocks agree with each other. Your heartbeat, your breath, the slow passing of night into morning all align into a steady rhythm that rarely surprises you. Time feels smooth, continuous, and impartial. Physics once believed this too. For centuries, time was treated as a universal backdrop, flowing evenly everywhere, independent of motion, gravity, or observation. Events happened in time, but time itself was untouched by events. It was the same for everyone, everywhere. That certainty did not survive the 20th century. Einstein showed us that time is not absolute. It stretches and contracts depending on motion and gravity. A clock moving quickly ticks more slowly than one at rest. A clock near a massive object ticks more slowly than one far away. These effects are small in everyday life, but they are real, measured, and unavoidable. Still, even with relativity, time remained smooth. It could slow down or speed up, but it never broke. Seconds still followed seconds. Cause still preceded effect. But near the Planck boundary, that smoothness begins to unravel. At extremely small scales, the same forces that destabilize space also destabilize time. Quantum fluctuations do not respect clean sequences. Energy spikes appear and vanish. Fields jitter unpredictably. And because time and space are woven together, instability in one bleeds into the other. Here, time no longer behaves like a steady river. It behaves more like a trembling surface. The idea of a precise instant becomes difficult to define. any attempt to isolate a moment injects energy into the system. That energy alters the geometry of spacetime. The now you are trying to capture shifts under the act of observation. Instead of a single, well-defined present, you encounter a haze of possibilities. This is not a limitation of perception. It is a physical effect. At these scales, uncertainty is not just about what you know. It is about what can be known. The laws themselves no longer guarantee a clean ordering of events. Cause and effect, which feel so fundamental, begin to blur. Normally, causes precede effects because time provides a clear direction. But when time fluctuates violently, that direction becomes less rigid. Events can no longer be cleanly labeled as before or after. They exist in overlapping probability clouds where sequence is not fixed until interactions settle. This does not mean that time runs backward in a dramatic way. It means that at the deepest levels, the concept of order becomes fuzzy. Processes do not unfold step by step. They overlap, interfere, and resolve only when averaged over larger scales. The familiar arrow of time, the sense that the past is fixed and the future is open, emerges only when these fluctuations cancel out. At the Planck scale, the arrow has not yet formed. This realization unsettles intuition because time feels more fundamental than space. You can imagine space bending or stretching, but imagining time itself losing coherence feels destabilizing. And yet, physics insists on it. Time, like space, may not be fundamental. It may be an emergent phenomenon, arising from deeper processes that do not themselves operate in time as we understand it. Consider temperature. At the level of individual molecules, temperature does not exist. There are only motions, collisions, energies. Temperature emerges only when you average over vast numbers of particles. It becomes meaningful at scale. Time may be similar. At the smallest scales, there may be no ticking clock, no flowing duration, only transitions, interactions, and correlations. Time appears only when these processes are viewed collectively, smoothed into a sequence that feels continuous. This would explain why time feels so stable at human scales and so fragile near the Planck boundary. The stability is not fundamental. It is statistical. This also helps explain why attempts to measure extremely small durations run into the same problems as attempts to measure extremely small distances. To define a very short interval of time, you need a very energetic process. That energy curves spacetime, altering the very interval you are trying to define. The clock disturbs itself. Below a certain threshold, the idea of a tick loses meaning. There is no clean division between one moment and the next. Duration becomes an approximation, not a fact. In this regime, the universe does not provide a universal now. Different regions may not agree on the ordering of events, even in principle. Temporal locality breaks down. This does not affect everyday life because these effects are confined to scales unimaginably small. By the time processes propagate upward into the scales you experience, time has already smoothed itself into a reliable flow. But at its core, time may be far more fragile than it appears. This fragility may also explain why physics struggles to unify gravity and quantum mechanics. Gravity treats time as part of a smooth geometric structure. Quantum mechanics treats time as an external parameter, a background against which change occurs. At the Planck boundary, neither treatment is sufficient. Time is too unstable to serve as a background, yet too entangled with geometry to be ignored. It resists being placed neatly into either framework. Some theories suggest that time does not exist at the deepest level at all, that the universe is fundamentally timeless, and that what we perceive as time is a byproduct of change, entropy, and information flow. In such views, the past and future are not intrinsic features of reality. They are perspectives that arise when systems evolve in certain ways. The universe does not march forward moment by moment. It simply is, with patterns that give rise to the sensation of flow. Near the Planck scale, those patterns dissolve. This does not mean that the universe becomes chaotic in a destructive sense. It means that the concepts we rely on, before, after, duration, are no longer the right tools. Time does not break dramatically. It frays quietly. and that quiet fraying has consequences. It suggests that the beginning of the universe, often imagined as a moment in time, may not have occurred in time at all. If time itself emerged from deeper processes, then asking what came before may be meaningless. It also suggests that the end of time, should such a thing exist, would not be a final moment, but a dissolution of sequence itself. These ideas are not conclusions, they are hints, whispers from equations pushed to their limits. As you rest here, allow yourself to feel how gentle this uncertainty is. The universe is not threatening to take time away from you. At the scales that matter for life, memory, and meaning, time remains steady and kind. It flows reliably enough for stories to exist, for sleep to come, for morning to follow night. But beneath that kindness lies a deeper truth. Time is not a rigid spine holding reality together. It is a pattern that emerges when chaos averages out, a rhythm born from countless fluctuations settling into order. And as we continue this quiet descent, one question naturally waits ahead. If time and space both lose their stability at the deepest scales, what happens when observation itself becomes too disruptive to proceed? Part 7. When observation changes reality. Too much. In most experiments, observation disturbs reality only slightly. Near the Planck scale, observation overwhelms it. The act of measuring injects so much energy that the system collapses, erasing the very information you hope to uncover. For much of science, observation feels almost innocent. You look, you record, you step back. The world continues as it was. A thermometer does not boil the water it measures. A telescope does not disturb the stars it observes. Even at the atomic level, many measurements feel gentle enough that their influence can be accounted for and corrected. This expectation runs deep. It is built into how we think about knowledge itself. We imagine that reality exists independently, waiting patiently to be examined. That observation reveals, rather than creates, that the universe is stable under our gaze, but physics has been quietly dismantling this assumption for more than a century. Quantum mechanics was the first to show that observation is not passive. To measure a particle's position is to disturb its motion. To measure its energy is to blur its timing. This disturbance is not a flaw in technique, it is a feature of reality. The act of observing changes the outcome. Still, at familiar scales, this disturbance is manageable. You can design experiments that minimize it. You can repeat measurements and recover stable patterns. The universe tolerates curiosity. Near the Planck scale, that tolerance disappears. Here, observation does not merely nudge reality, it overwhelms it. To understand why, it helps to remember what measurement actually requires. To observe something, you must interact with it. Information does not travel for free. It is carried by particles, waves, exchanges of energy, and momentum. If you want fine detail, you must use a probe with fine resolution. And fine resolution demands high energy. This trade-off is unavoidable. It is not a limitation of technology. It is written into the structure of waves, particles, and information itself. At modest scales, the energy required is small enough that its side effects are negligible. But as you aim for ever smaller targets, the required energy rises sharply. Eventually, it becomes enormous. Near the Planck boundary, the energy needed to resolve a region becomes comparable to the energy that shapes spacetime itself. At that point, observation stops being a window and becomes a force. When you inject that much energy into such a tiny region, the region does not remain intact. Space curves inward. Time distorts. The geometry collapses. The system you hope to study is fundamentally altered by the act of studying it. This is not measurement uncertainty in the usual sense. It is not about noise or imprecision. It is about self-destruction. The question becomes too heavy to survive. In everyday physics, we often talk about back reaction, the idea that a system responds to being measured. Near the Planck scale, back reaction dominates everything. The system does not merely respond, it reorganizes itself entirely. In extreme cases, it disappears behind a boundary from which no information can return. The measurement creates its own blind spot. This creates a profound paradox. To learn more, you must look harder. To look harder, you must use more energy. To use more energy, you destroy the very structure you want to understand. There is no clever workaround. You cannot measure gently because gentle probes are too coarse. You cannot measure forcefully because force collapses the system. You are trapped between ignorance and annihilation of information. This is where the universe draws its most subtle boundary, not by forbidding questions, but by ensuring that certain questions erase their own answers. At this scale, the classical idea of an observer standing outside the system collapses. There is no outside. The observer is part of the interaction, and the interaction reshapes reality itself. This challenges the deepest assumptions of objectivity. In classical science, you can imagine an ideal observer who does not interfere. At the Planck scale, such an observer cannot exist. Any observer powerful enough to extract information is powerful enough to change the system beyond recognition. Knowledge becomes inseparable from influence. This realization forces physics into a humbler posture. It suggests that there are limits not just to what we can measure, but to what can meaningfully be measured at all. Some quantities may exist only in approximation. Some structures may be inherently inaccessible to direct observation. This does not mean they are unknowable in principle. It means they cannot be known directly. Instead, they must be inferred indirectly through their effects at larger scales where observation is gentler and spacetime remains stable. This is why much of modern theoretical physics relies on consistency, symmetry, and mathematical necessity rather than direct measurement. The deepest layers of reality may only reveal themselves through how they constrain what is possible above them. The Planck scale is not illuminated by experiments, it is outlined by consequences. There's also something quietly philosophical here. Observation, which feels like a passive act of curiosity, turns out to be a creative force. At small enough scales, to observe is to participate, to know is to change. This is not a failure of science. It is a reminder that science is a dialogue with the universe, not a one-sided interrogation. The universe responds to how we ask. And when we ask too sharply, too forcefully, it responds by closing the conversation. There is a gentle wisdom in this. Reality is not infinitely delicate. It does not allow itself to be peeled apart layer by layer without consequence. It maintains coherence by limiting access to its most volatile regimes. This may be why the Planck boundary feels so final. It is not merely a technical limit, it is a relational one. It marks the point where the relationship between observer and observed breaks down. Beyond it, the distinction between question and answer dissolves. As you rest now, consider how different this is from everyday experience. You can look at a tree without altering it. You can measure the length of a room without collapsing the walls. The universe allows you to explore freely at the scales you inhabit. Only when curiosity presses against the deepest foundations does resistance appear. And even then, the resistance is quiet. There is no alarm, no explosion, just silence where answers might have been. This silence is not emptiness, it is protection. It ensures that space-time does not tear itself apart under the weight of infinite scrutiny. It preserves the stability that allows stars to shine and thoughts to form. In this way, the limits of observation are also the conditions for existence. If observation could probe arbitrarily deep without consequence, reality would be infinitely fragile. Every question would risk collapse. No structure could endure. By imposing a limit, the universe allows complexity to persist. And so, when observation changes reality too much, it is not punishing curiosity, it is preserving coherence. As we continue this slow, careful journey, one question gently emerges from the quiet. If observation itself becomes impossible at the deepest scales, what then lies beneath what we can ever directly see? Part 8. Quantum foam beneath everything. Beneath atoms, beneath particles, beneath fields, space-time itself may boil with constant microscopic fluctuations. Tiny regions appear and vanish. Curvature forms and dissolves. Reality becomes probabilistic at the level of space itself. When you imagine empty space, you probably imagine stillness, a vast, silent nothing where nothing happens unless something enters. This image is comforting in its simplicity. Space feels like absence, like a blank canvas waiting to be filled. Physics once agreed. For a long time, empty space was treated as truly empty. Remove all matter, all light, all motion, and you were left with nothing at all. A void, a perfect background. But as experiments grew more precise, this picture quietly fell apart. Quantum physics revealed that even the emptiest space is restless. Fields cannot settle into perfect calm. Energy flickers in and out. Particles briefly appear, then vanish again, too quickly to be directly observed, yet influential enough to leave measurable traces. This activity does not happen in space alone. It may happen to space. Near the Planck boundary, spacetime itself joins the dance. Here, space is no longer a smooth arena hosting fluctuations. It becomes a participant, fluctuating along with everything else. The geometry you rely on to define direction and distance is itself unstable, forming and dissolving in an endless microscopic churn. Physicist John Wheeler gave this behavior a name: quantum foam. Not because it looks like bubbles in any literal sense, but because it captures the idea of constant, frothy change. At unimaginably small scales, spacetime may resemble a stormy sea of transient structures, where no configuration lasts long enough to be called permanent. This regime, space is not a fixed thing, it is a process. Tiny regions of curvature spontaneously form, twist, and collapse. Connections between points fluctuate. Even the basic notion of continuity breaks down. What you think of as a smooth surface is replaced by a constantly rearranging network. This is not chaos in the everyday sense. It is structured unpredictability, governed by probabilities rather than certainties. At larger scales, these fluctuations average out. Their effects cancel. Space appears smooth again, just as the random motion of air molecules averages into a steady pressure. But at the smallest scales, there is nothing large enough to do the averaging. The foam is all there is. This idea challenges one of our most basic assumptions, that space exists independently of what fills it. In the quantum foam picture, space is inseparable from activity. There is no empty backdrop waiting passively. There is only ongoing fluctuation. Even the idea of nothing dissolves. What we call vacuum is not the absence of everything. It is the lowest energy state of a set of fields that can never fully rest. Those fields interact. They exchange energy. They create momentary structures that leave subtle imprints on the universe above them. Casimir forces, vacuum polarization, shifts in atomic energy levels. These are gentle echoes of the foam, felt far above the scale where it originates. But near the Planck scale, the foam itself dominates. Here, probabilities replace certainties not just for particles, but for geometry. Space does not have a definite shape. It has a distribution of possible shapes. Time does not have a single duration. It has a spread of possibilities. Reality becomes statistical at its foundation. This does not mean that the universe becomes random in a careless way. The probabilities are constrained. They follow precise mathematical rules. Patterns emerge, even if individual configurations are fleeting. Think of a crowd viewed from far above. From a distance, the crowd looks smooth and continuous. From close up, it is a sea of individuals constantly moving, adjusting, colliding, separating. No single arrangement lasts long, but the overall structure remains stable. Quantum foam may be like that, ceaseless microscopic motion giving rise to macroscopic calm. This perspective helps explain why space-time resists being probed too finely. You are not trying to examine a solid object, you are trying to freeze a storm. Any attempt to pin down a specific configuration injects energy, altering the probabilities, reshaping the foam. The more precisely you look, the more violently the structure responds. Observation becomes intrusion. This also reframes the question of what space-time is. It may not be a thing made of smaller things. It may be a behavior, an emergent pattern arising from deeper rules that do not resemble geometry at all. Some theories suggest that at the deepest level, reality is composed of abstract relationships, connections, interactions, information exchanges. Space and time emerge when these relationships organize in certain ways. In such views, the foam is not space breaking down, it is space failing to fully emerge. Geometry, distance, and duration crystallize only when the underlying activity settles into a stable pattern. At the Planck scale, that settlement never happens. This idea is unsettling because it removes the comforting solidity of space. There is no ultimate floor you can stand on, no final layer of smoothness beneath which everything is simple. Instead, there is motion all the way down. And yet, this motion is not hostile. It is what allows flexibility, adaptation, and stability at higher levels. The foam absorbs extremes, it diffuses singularities, it prevents infinite compression. Without this restless foundation, spacetime might shatter under its own equations. The foam acts as a buffer, a dynamic cushion that smooths out the violent tendencies of gravity and quantum uncertainty. In this sense, the universe's deepest turbulence is what allows its largest structures to endure. There's a quiet beauty in that. Chaos beneath order, uncertainty beneath reliability, motion beneath stillness. As you lie here, breathing slowly, imagine this hidden sea beneath everything you know. Not threatening, not noisy, just endlessly active in a way that never rises high enough to disturb the surface you inhabit. Your body rests on a planet that orbits a star, that moves through a galaxy, that drifts through space-time. Beneath all of that, space-time itself flickers, too small and too fast to ever be felt. You are sheltered by scale. This realization can feel strangely comforting. It suggests that reality is not brittle. It does not depend on perfect stillness to function. It thrives on fluctuation as long as those fluctuations remain balanced. Quantum foam is not a flaw to be eliminated. It is a feature that makes coherence possible, and yet it also marks a boundary for understanding. We can describe the foam mathematically. We can infer its presence through effects at larger scales, but we cannot directly observe it. Any attempt to do so collapses the very structure we seek. So the foam remains hypothetical, inferred, whispered by equations rather than seen by instruments. It stands as a reminder that some aspects of reality may always remain indirect, glimpsed only through their influence. As this part of the journey settles, another question begins to form, soft and patient. If space-time itself is made of probabilities and fluctuations, what happens to geometry when these fluctuations no longer average out at all? Part 9. Why light can no longer help us. Light has always been our messenger, but at this boundary, even light becomes too crude. Its energy either smears out detail or collapses space-time entirely. The universe closes its eyes to photons at its smallest scales. From the very beginning of science, light has been how we learn to see, not just with our eyes, but with our instruments, our equations, and our understanding. Light reflects off surfaces, carries information across space, and arrives faithfully at detectors that translate it into knowledge. From candle flames to lasers, from telescopes to microscopes, light has been our most trusted guide. It feels natural to assume it will always be enough. After all, light reveals galaxies billions of years old. It maps the structure of atoms. It measures distances across the universe with astonishing precision. Even time itself is defined by the oscillations of light trapped in atomic clocks. Light seems inseparable from knowing. But as we approach the deepest scales of reality, this trust quietly breaks down. The limitation is not technological. It is not because our lenses are imperfect or our detectors too slow. It is because light itself has a nature that prevents it from going any further. To understand why, we need to return to something simple and easily forgotten. Light is a wave, and it is also a carrier of energy. Every wave has a wavelength. That wavelength sets the smallest detail it can resolve. Long wavelengths wash over small structures without noticing them. Short wavelengths reveal finer detail. This is why visible light can show you cells but not atoms, and why X-rays can reveal atomic spacing but not subatomic structure. So to see smaller things, you shorten the wavelength. Shortening the wavelength means increasing the energy. This is where the trouble begins. At first, the trade-off seems acceptable. Ultraviolet light reveals finer detail than visible light. X-rays reveal more still. Gamma rays push even further. Each step uses photons that carry more energy, and each step risks damaging what you are trying to observe. But near the Planck boundary, the required energy becomes extreme. A photon with a wavelength small enough to probe those scales carries so much energy that it no longer behaves like a gentle probe. It becomes an event. When such a photon enters a tiny region of space, its energy density skyrockets. Space responds, it curves, it compresses, and if the energy is concentrated enough, that region collapses inward. The photon does not illuminate the structure, it erases it. This is the paradox of light at the smallest scales. If the energy is too low, the wavelength is too large, and all fine detail is smeared away. If the energy is too high, spacetime itself reacts violently, hiding the region behind gravitational collapse. Light can neither whisper nor shout without consequence. There is no just right setting. This is not because photons are flawed. It is because spacetime itself enforces a limit on how sharply it can be interrogated. Light, which has served us so faithfully across every other scale, simply does not fit the conditions here. Its dual nature, wave and energy carrier, becomes an obstacle rather than a tool. At the Planck boundary, the universe becomes opaque to light, not because it absorbs photons, but because the act of sending them destroys the context needed for information to return. In a sense, spacetime turns inward. It stops acting like a transparent medium and becomes self-protective. The usual relationship between light and knowledge breaks down. This is deeply counterintuitive because light feels synonymous with understanding. We speak of illumination, insight, clarity. Light is woven into our metaphors for truth. Yet here, truth persists without illumination. The universe does not go dark because there is nothing there. It goes dark because seeing is no longer the right way to know. This realization forces a quiet humility. Every era of science has believed that its tools were nearly sufficient, that one more refinement would complete the picture. But light, the most refined messenger we have ever known, reaches a point where it can no longer speak for us. This does not mean that smaller scales are unknowable. It means they are not photographable. They cannot be lit up and imaged the way we image galaxies or cells. They must be approached indirectly through inference, consistency, and mathematical structure. We learn about them not by shining light, but by listening to consequences, the behavior of particles, the stability of space-time, the absence of infinities. These are the faint shadows cast by something deeper, something light cannot touch. There is something oddly peaceful about this. It means that reality does not demand to be seen in order to exist. It does not perform for observation. It does not reveal itself on command. Instead, it sets conditions. At the scales where life unfolds, light is welcomed. It travels freely. It carries stories across the cosmos. At the scales where space-time itself is being defined, light is politely turned away. The universe draws a boundary not with violence, but with silence. This boundary also explains why our most advanced theories rely less on visualization and more on abstraction. At these depths, diagrams fail, pictures mislead, geometry becomes unreliable. What remains are relationships, symmetries, constraints. Light once told us where things are. At the Planck scale, where loses meaning. Light once told us when events happen. Here, when phrase. So light steps aside. And in doing so, it reminds us that our senses, even when amplified by technology, are not universal translators. They evolved for a narrow range of scales, and even our best instruments extend them only so far. Beyond that, the universe speaks a different language. One of mathematics, one of probability, one of structure without shape. This is not a loss, it is a transition. Just as sound fails in the vacuum of space, but radio waves continue. Light fails at the Planck boundary while other forms of understanding persist. The universe is not hiding. It is changing the terms of conversation. As you rest here, imagine this gently. A place so small that even light cannot enter. Without causing collapse, a region that does not reflect, scatter, or transmit photons in any meaningful way. Not dark, but unseeable. This is not emptiness, it is density beyond illumination. And perhaps this is fitting. The deepest layers of reality are not meant to be observed the way surfaces are. They are not meant to be lit from the outside. They are the conditions that allow light itself to exist. Light emerges from spacetime. It cannot define spacetime at its birth. And as this realization settles, another question begins to glow softly in the background. If light can no longer guide us, what tools, if any, remain for understanding what lies beyond this boundary? Part 10. Gravity and Quantum Theory. Disagree. Quietly everywhere else, our theories work beautifully. But here, gravity and quantum mechanics speak incompatible languages. Their equations cannot coexist at this scale, leaving physicists with two partial truths and no shared grammar. For most of modern physics, this division has been easy to ignore. Quantum mechanics governs the smallest things with astonishing accuracy. It predicts the behavior of atoms, electrons, and fields to more decimal places than any other theory in science. General relativity governs the largest things just as precisely. It explains the motion of planets, the bending of light by stars, and the slow dance of galaxies across the cosmos. Each theory reigns supreme in its own domain. Like two maps drawn at different scales, they overlap just enough to appear compatible, but never enough to reveal their contradictions. As long as the very small stays light and the very massive stays large, the universe behaves politely. Each theory minds its own business. But near the Planck boundary, those domains collide. Here, distances are so small that quantum effects dominate. At the same time, energies are so high that gravity cannot be ignored. This is the rare place where both theories are demanded at once, and neither can fully function. Quantum mechanics assumes a fixed stage. It describes particles and fields evolving against a stable background of space and time. The geometry is given. The clock ticks steadily. Probabilities unfold within a known framework. General relativity assumes the opposite. It insists that space and time are not fixed at all. They are dynamic, shaped by energy and momentum. There is no universal clock, no rigid grid. Geometry is the outcome, not the starting point. Each theory is internally consistent. Each has passed every experimental test thrown at it, but they make opposite assumptions about the very thing they are both trying to describe. At ordinary scales, this disagreement is invisible. Quantum effects average out in large systems. Gravitational curvature becomes negligible at small masses. The universe gives us plenty of room to pretend the conflict does not exist. But at the Planck scale, there is no room left. Here, spacetime must fluctuate quantum mechanically, yet also respond smoothly to energy. Time must be uncertain, yet also define evolution. Space must be both discrete and continuous. Each demand cancels the other. The equations simply stop agreeing, not explosively, not dramatically, quietly. Terms diverge, predictions contradict. Mathematical infinities appear where none should exist. The language of one theory cannot be translated into the other. This is not because physicists lack creativity. It is because the foundational assumptions are incompatible. Quantum mechanics treats uncertainty as fundamental. It allows superpositions, probabilities, and indeterminacy at the deepest level. General relativity treats geometry as precise, continuous, and deterministic. It assumes spacetime has exact curvature at every point. When you try to quantize gravity using the tools of quantum theory, spacetime fractures into uncontrollable infinities. When you try to force quantum uncertainty into curved spacetime, the concept of time evolution loses meaning. Each theory resists assimilation, and yet both are clearly describing the same universe. This is what makes the disagreement so haunting. It is not an argument over data. It is not a dispute about interpretation. It is a clash of structure. It suggests that something deeper lies beneath both frameworks, something neither fully captures. Physicists sometimes describe this situation as standing between two cliffs, shouting across a gap too wide to bridge with current tools. On one side, quantum mechanics whispers of probability, discreteness, and indeterminacy. On the other, general relativity speaks of smooth curves, continuity, and geometric elegance. They agree on outcomes everywhere except where it matters most, near black hole horizons, at the beginning of the universe, at the Planck boundary. In those places, their quiet disagreement becomes unavoidable. Consider the fate of information near extreme gravity. Quantum mechanics insists that information is preserved. General relativity allows spacetime regions where information appears to be lost forever. Each position is supported by deep reasoning. Both cannot be correct in the same way. Or consider time. Quantum mechanics treats time as an external parameter. General relativity treats time as a coordinate that can stretch, bend, and even end. When spacetime itself fluctuates, which notion of time survives? The theories do not answer each other. They talk past each other. This has led physicists to suspect that neither theory is fundamental. Perhaps quantum mechanics is an approximation that works when spacetime is calm and smooth. Perhaps general relativity is an approximation that works when quantum fluctuations are negligible. And perhaps both emerge from a deeper structure that does not resemble either. If so, the disagreement is not a failure, it is a clue. It tells us that our current languages are too specialized. Each captures part of the truth, but neither captures the whole. This realization has reshaped how physicists think about unification. The goal is no longer to force gravity into quantum mechanics or vice versa. It is to find a new framework where both emerge naturally, without contradiction. Such a framework would not treat space and time as fundamental. It would not assume smooth geometry or fixed backgrounds. It would describe reality in terms that make both quantum uncertainty and gravitational curvature inevitable consequences. What those terms are, we do not yet know. Some proposals speak of discrete structures, networks of relationships, or fundamental units of information. Others imagine geometry emerging from entanglement, or spacetime arising from deeper algebraic rules. These ideas are not yet confirmed. They are attempts to listen for a language beneath the disagreement. What is striking is how gentle this failure is. Physics does not collapse at the Planck boundary in a blaze of contradiction. It simply stops being coherent. Predictions lose precision. Equations lose meaning. The theories remain beautiful within their domains, but cannot step beyond them. The universe does not punish us for this limitation. It merely withholds agreement. There is something deeply human about this. We often assume that understanding must be unified, seamless, complete, that contradictions signal error, but sometimes contradictions signal scale. They tell us that a description valid in one context cannot simply be stretched into another. Gravity and quantum mechanics disagree not because one is wrong, but because both are incomplete. And that incompleteness is not a flaw in science. It is a reflection of how knowledge grows by discovering the edges of its own language. As you rest here, imagine these two theories as calm, patient narrators describing the same landscape from opposite sides. Each sees clearly where they stand. Neither can see the whole terrain alone. Between them lies a valley still covered in mist. The Planck boundary marks where the mist thickens, where familiar shapes dissolve, where the terrain no longer matches the map. This is not a place of failure. It is a place of invitation, an invitation to rethink what space is, what time is, what it means for something to exist at all. Until that invitation is answered, physics lives with a quiet tension, a respectful disagreement that does not shout, does not resolve, and does not go away. And perhaps that is fitting, because the universe itself seems content with partial truths, with layered descriptions that work where they are needed, with no obligation to fit neatly into a single story. As this part of the journey settles, one final question begins to surface, steady and unhurried. If our deepest theories cannot yet speak to each other, what kind of language could possibly unite them? Part 11. The smallest meaningful moment. Just as there is a smallest length, there may be a smallest unit of time. Below it, the concept of before and after dissolves. Events no longer unfold smoothly, but flicker into existence without sequence. In daily life, time feels endlessly divisible. A minute can be split into seconds, a second into milliseconds, milliseconds into microseconds, and so on without apparent limit. Our clocks encourage this belief. With each advance in technology, we slice time more finely, confident that there is always another decimal place waiting. For most of physics, this assumption worked beautifully. Time was treated as a continuous flow, a river that could be sampled at any point. Whether slow or fast, stretched or compressed, it always moved forward in an unbroken line. Even when relativity taught us that time depends on motion and gravity, it remained smooth. A slowed clock still ticked. A stretched second still had structure. But as physics follows its own logic toward the deepest scales, this smoothness begins to fray. At extremely small intervals, the same forces that destabilize space also destabilize time. The equations suggest that there may be a shortest meaningful duration, a smallest tick that cannot be subdivided without losing coherence altogether. Below this scale, time does not flow, it flickers. To understand why, it helps to ask what it really means to measure time. A clock is not an abstract concept, it is a physical system. It relies on motion, oscillation, or decay, something changing from one state to another. A pendulum swings, an atom vibrates, a particle decays. Time is inferred from change, but change itself requires energy. And at very small timescales, defining a shorter and shorter interval demands higher and higher energy transitions. Just as with space, precision comes at a cost. If you want to resolve an extremely brief moment, you must use a process energetic enough to mark that moment distinctly. But that energy disturbs the system, altering the very duration you are trying to define. At some point, the disturbance becomes total. The energy required to define a smaller slice of time becomes so intense that spacetime itself responds. Geometry fluctuates. Cause and effect blur. The notion of a clean sequence collapses. This is where the idea of a smallest meaningful moment arises. It is not that smaller durations cannot exist. It is that they cannot be defined in any operational sense. There is no physical process that can mark them reliably, no clock that can tick faster without destroying the context needed for ticking. Below this threshold, moment stops being a useful word. The universe does not provide a finer grain of time for events to occupy. Instead, events smear into a haze of possibilities. They do not occur at a time so much as across a range of potential orderings. This challenges one of our deepest intuitions, that time is the stage on which everything else happens. At the smallest scales, time may not be a stage at all. It may be a byproduct. Some physicists suspect that time emerges only when systems become large enough and complex enough for sequences to stabilize. At the deepest level, there may be no universal clock ticking away, only correlations, one interaction relating to another without a fixed temporal order. In such a picture, before and after are not fundamental. They arise when the universe is coarse-grained, when countless microscopic events are averaged into a macroscopic flow. This is similar to how direction emerges in thermodynamics. On the level of individual particles, motion is reversible. But when many particles interact, entropy increases and an arrow of time appears. The smallest meaningful moment may mark the scale at which this arrow first becomes possible. Below it, time has no direction, it has no flow, it has no sequence. Events do not line up like beads on a string. They overlap, interfere, and resolve only when viewed from a higher level where averaging restores order. This does not mean that reality becomes chaotic in a destructive sense. It means that it becomes relational rather than sequential. Instead of events happening one after another, they are linked in networks of influence where order is not absolute. What matters is not when something happens, but how it connects to something else. This idea can feel unsettling because time feels so personal. Memories rely on sequence. Identity relies on continuity. Life itself feels inseparable from the passage of moments, but it is important to remember that this breakdown occurs far below any scale relevant to experience. By the time processes reach the level of neurons, heartbeats, and thoughts, time has already stabilized into a reliable flow. The smallest meaningful moment is unimaginably brief. It does not intrude into daily life. It does not interrupt sleep, memory, or motion. It simply marks the boundary where our familiar concept of time stops applying. And this boundary may be essential. Without it, physics predicts infinities, Processes could occur infinitely fast. Cause and effect would collapse into paradox. Stability would vanish. By enforcing a minimum duration, the universe preserves coherence. It ensures that change happens in steps that can be related, rather than dissolving into instantaneous chaos. This minimum does not feel like a limitation when viewed this way. It feels like a foundation. It tells us that time, like space, has texture, that it is not an infinitely smooth line, but something with grain, something that emerges from deeper activity. In this sense, the smallest meaningful moment is not a ticking clock. It is a pause that prevents reality from collapsing into contradiction. As you breathe now, notice how your own sense of time softens. Thoughts slow. Moments blur gently into one another. Sleep approaches not as a sudden event, but as a gradual settling. This is not the Planck scale, of course, but it offers a hint of how time can feel less rigid without disappearing entirely. The universe may experience something similar at its deepest level, not rushing from instant to instant, but existing in a state where sequence is optional, where change is not forced into a strict order. Only when scale increases, when complexity builds, does time organize itself into the flow you recognize. This perspective also reshapes how we think about beginnings. If there is a smallest meaningful moment, then the origin of the universe may not be a point in time at all. The earliest state may exist outside of time as we understand it, with temporal order emerging only afterward. Asking what happened before may be like asking what is north of the North Pole. The question assumes a structure that does not apply. This does not diminish the mystery, it deepens it. It suggests that time is not the container of reality, but one of its creations. And like all creations, it has limits. As this idea settles gently, another question begins to take shape, waiting just beyond the edge of this moment. If time itself emerges only above a certain scale, what does existence look like where even moments cannot form? Part 12. Why the universe protects its secrets. The Planck boundary may not be a flaw, but a safeguard, a natural barrier that prevents infinite density, infinite information, and infinite precision. The universe may be protecting itself from paradox. At first, this idea feels almost unsettling. We are taught to think of limits as failures, places where understanding breaks down because we lack the right tools, the right insight, or the right perseverance. In science especially, boundaries are often seen as invitations. Push harder, look deeper, refine the measurement. Eventually, the truth will yield. But the Planck boundary does not behave like an invitation. It behaves like a quiet refusal, not a dramatic one. There is no warning sign, no violent reaction. The universe simply stops answering in the way it used to. Equations lose their predictive power. Measurements collapse into uncertainty. Concepts that once felt solid, distance, duration, location, begin to blur. And yet, when physicists look closely, this refusal appears strangely deliberate. Everywhere else, the universe allows extremes. Stars grow unimaginably dense. Temperatures reach millions of degrees. Energies climb to astonishing heights. But at the deepest scales, something intervenes. Something prevents the universe from being pushed into infinite sharpness. This is not arbitrary. Infinite quantities are poison to physical law. An infinite density means gravity becomes uncontrollable. An infinite energy concentration means space-time tears itself apart. An infinite amount of information packed into a finite region would destroy causality, making prediction meaningless. If infinities were allowed to exist freely, the universe would not be stable enough to host anything complex. There would be no atoms, no stars, no long-lived structures. Reality would collapse into mathematical contradiction. The Planck boundary stops that from happening. It ensures that no region of spacetime can be probed beyond a certain precision. It enforces a maximum density of information. It prevents energy from being compressed without consequence. In doing so, it protects consistency. This is why many physicists no longer view the Planck scale as a problem to be eliminated, but as a feature to be understood. The boundary is not a sign that the universe is unfinished, it is a sign that it is self-regulating. Much like biological systems impose limits to remain stable, heartbeats within a range, temperatures within a window, the universe imposes limits on how extreme its own properties can become. Too much precision becomes destructive. Too much information collapses the structure that carries it. So the universe gently says no. There is a parallel here with something deeply familiar. Think about sleep itself. Consciousness fades not because the brain fails, but because it protects itself. Endless wakefulness would be damaging. Rest is enforced by biology to preserve coherence. Boundaries are not weaknesses, they are safeguards. The Planck boundary may serve a similar role for reality. It prevents infinite scrutiny from unraveling the fabric of existence. This perspective reframes the deepest mysteries of physics. Instead of asking why we cannot see beyond the boundary, we begin to ask why the boundary exists at all. What is it preserving? What instability does it prevent? One answer seems increasingly clear: paradox. Without a smallest length, quantum fluctuations could create infinite curvature everywhere. Without a smallest time, causality would dissolve into loops with no order. Without limits on information density, black holes would violate the consistency of physical law. The universe avoids these outcomes not through complexity, but through restraint. It does not allow you to ask questions that would destroy the conditions required for answers. This is not an act of concealment, it is an act of preservation. There is something quietly elegant about this. Reality is not infinitely fragile. It does not allow itself to be pulled apart thread by thread until nothing remains. It has built-in protections that maintain its integrity across scales. And these protections do not feel forced. They arise naturally from the interplay of quantum uncertainty and gravity, from the fact that energy has weight, from the fact that observation requires interaction, from the fact that information is physical. The universe does not need an external rule to prevent infinities. Its own structure enforces the limit. This also explains why so many attempts to unify physics encounter the same barrier. Whenever a theory tries to remove the boundary by allowing arbitrary precision or infinite resolution, it runs into contradiction. Whenever a theory respects the boundary, consistency improves. It is as if the universe is guiding theory by refusal rather than instruction. Some answers are not given, they are ruled out. And in that ruling out, clarity emerges. This does not mean that the universe is hiding something maliciously. It means that not all questions are well posed. Some questions assume conditions that reality will not allow. Asking what exists beyond the Planck boundary may be like asking what is north of the North Pole. The question presumes a framework that no longer applies. The universe protects itself by dissolving the framework. There is a humility required to accept this. Science is not defeated by such limits. It is refined by them. Understanding shifts from accumulation of detail to respect for structure, from endless dissection to recognition of coherence. The Planck boundary reminds us that reality is not infinitely reducible. It is layered, contextual, and internally consistent. And this consistency is what allows wonder. If the universe allowed infinite detail, it would collapse into noise. Nothing would stand out, nothing would endure. Limits create contrast. They create structure. They allow patterns to persist. The stars shine because gravity is strong but not infinite. Atoms exist because electromagnetic forces are precise but bounded. Time flows because change is ordered, not chaotic. The deepest limit protects all the others. As you rest here, breathing slowly, consider this not as a barrier but as a quiet promise. The universe is not a puzzle with an infinitely sharp solution. It is a system designed to remain whole. It allows mystery not because it is incomplete, but because it is stable. And perhaps that is why these questions feel strangely calming rather than frustrating. There is reassurance in knowing that reality has depth without requiring infinite exposure, that some aspects of existence are protected, not withheld. The night sky does not reveal every star to the naked eye, yet its beauty is not diminished. In fact, the unseen adds to the wonder. The Planck boundary may serve the same role at the deepest level. It ensures that reality retains a horizon. a place where knowledge transitions into humility, where explanation gives way to respect. And as this thought settles gently, one final question drifts into view, waiting patiently. If the universe protects itself so carefully, what kind of reality emerges on the safe side of that boundary, where life and meaning are allowed to exist? Part 13. Echoes of the first instant. This boundary mirrors conditions that existed at the birth of the cosmos. The same physics that blocks us today governed the universe's earliest moments. In trying to see smaller, we brush against the beginning of everything. When physicists speak about the origin of the universe, they often describe it as a beginning in time, a moment when everything started, a first tick of the cosmic clock. But as you drift closer to the Planck boundary, that familiar picture begins to soften. The equation suggests something more subtle. The earliest universe was not simply small. It was governed by the same rules that now prevent us from looking any deeper. In other words, the wall we encounter at the smallest scales is not new. We have been here before, at the very beginning. In the first unimaginably brief interval after the universe came into being, conditions were extreme beyond anything we can recreate. Space was compressed to its limits, energy densities were enormous, temperatures soared beyond comprehension, and the distinctions we rely on between space and time, between particles and fields, between cause and effect, had not yet fully formed. The universe existed in a state where our familiar laws were not yet separated. Gravity, electromagnetism, and the nuclear forces were once unified, indistinguishable from one another. Space and time were tightly bound, fluctuating violently. Quantum uncertainty and gravitational curvature were equally dominant. This was not a smooth expansion from a point. It was a regime where geometry itself was uncertain. This is why modern cosmology and Planck-scale physics are so deeply intertwined. When we push our theories inward toward smaller and smaller distances, we are not merely exploring the microstructure of reality. We are retracing the conditions of the universe's first moments. The same breakdowns we encounter now, the loss of smooth spacetime, the failure of classical measurement, the incompatibility of our theories, are echoes of that earliest era. The Planck boundary is not just a limit of observation, it is a memory. In the first fraction of a second after the universe began, there was no calm background in which events unfolded. There was no fixed distance between points, no steady flow of time. The universe was not a stage with actors, it was a single inseparable process. As it expanded and cooled, structure emerged, forces differentiated, space smoothed out, time gained direction, particles acquired identity. What we now experience as a stable universe gradually crystallized from that primal turbulence. The fact that we cannot probe beyond the Planck scale today suggests that this crystallization left behind a permanent boundary, a boundary that still marks where space-time itself was born. When we try to look smaller, we are not just asking about substructure, we are asking to revisit conditions where smaller had no meaning yet. This reframes the idea of the Big Bang in a profound way. Rather than a point exploding into space, the beginning may have been a transition, a phase change in the nature of reality itself. A shift from a timeless, non-geometric regime into one where space and time became meaningful concepts. The Planck boundary may be the fossil edge of that transition. Beyond it, the universe did not yet have the properties we rely on to describe it. There were no distances to measure, no durations to count, no paths for light to follow. Asking what happened before becomes problematic, because time itself may not have existed in the way we understand it. This is why physicists are careful when they speak about the beginning. The equations do not describe a clean starting moment. They describe a domain where the language of moments fails. In this view, the Planck scale is not just the smallest scale of space, it is the smallest scale of meaningful history. Below it, events do not line up into a narrative. They do not unfold. They simply are. This may explain why every attempt to unify quantum mechanics and gravity inevitably circles back to the early universe. The same conceptual obstacles appear. The same mathematical tensions arise. The same questions refuse to be answered in familiar terms. The universe is telling us something quietly but persistently. The beginning is not behind us in time, it is beneath us in scale. Every time we attempt to sharpen our view beyond the Planck boundary, we encounter the same conditions that once governed everything. Conditions so fundamental that they never fully disappeared. They were merely hidden beneath the smoothness of expansion. In that sense, the earliest universe is not gone. It is folded into the foundation of reality. This idea carries a strange comfort. It means that the birth of the cosmos was not a singular, inaccessible event locked forever in the past. It is a regime that still exists, still influences what is possible, still shapes the limits of knowledge. We live in a universe that remembers how it began. That memory is encoded not in pictures or relic radiation alone, but in the very structure of spacetime, in the fact that distances cannot shrink arbitrarily, in the fact that time cannot be divided endlessly, in the fact that gravity and quantum mechanics still refuse to merge cleanly. These are not failures, they are signatures. They tell us that reality emerged from something deeper than geometry, deeper than particles, deeper than time, and that emergence left boundaries behind. When cosmologists study the early universe, they rely on indirect evidence, patterns in cosmic radiation, distributions of galaxies, subtle imprints of ancient fluctuations stretched across billions of light years. These observations tell a story of rapid expansion, of cooling, of structure forming from tiny irregularities. But the story always stops short of the very beginning. Not because data is missing, but because the concept of beginning dissolves at the Planck boundary. This is why the Planck time, the smallest meaningful interval, appears in cosmology. It marks the point beyond which our descriptions lose coherence, not because nothing existed, but because existence itself had not yet taken the shape we recognize. The universe did not start ticking like a clock at zero. It transitioned into a state where ticking became possible. In trying to peer past the Planck Wall, we are not being blocked arbitrarily. We are being reminded that some questions presuppose conditions that did not yet exist. This realization changes how we think about origins. Instead of asking what came before the universe, we may need to ask how the universe learned to have a before it all. How time acquired direction, how space acquired dimension, how causality emerged from a causal substrate. These are not questions that can be answered by looking harder or building larger machines. They require new ways of thinking, new mathematical languages, new intuitions, and perhaps patience. As you rest here, let this perspective settle gently. The Planck boundary is not just a wall in the small, it is a mirror reflecting the large, a reminder that the deepest limits of physics are tied to the first moments of existence. We cannot cross this boundary, because to do so would require stepping into a regime where our questions no longer apply, and that may be exactly as it should be. Because the universe did not begin in terms meant for us, it evolved into them. Space, time, light, and matter are not the starting point. They are the outcome. And as we continue this quiet journey toward understanding, one final thought begins to emerge, soft and unresolved. If the Planck boundary marks both the smallest scale and the first moment, what does that tell us about why the universe has limits at all? Part 14. What theories still whisper? Though experiments fall silent, mathematics continues to whisper possibilities. Strings, loops, discrete geometry. These ideas suggest that space itself may be built from something deeper, something countable rather than continuous. When observation reaches its limit, physics does not stop thinking. It grows quieter instead. The instruments power down, the detectors fall silent, but the equations remain. Symbols still relate to one another. Patterns still hint at structure. Even when nature refuses to be measured directly, it may still be described, softly, through mathematics. This is where modern physics now finds itself. At the Planck boundary, experiments can no longer guide us forward. No accelerator can reach those energies. No telescope can peer into that scale. Light cannot carry messages back. And yet, the universe has left clues behind, scattered across the behavior of everything above that boundary. Mathematics becomes the language of inference, not the mathematics of calculation alone, but the mathematics of consistency. of asking not, what do we see, but what must be true for everything we see to work at all. In this quiet space, theories begin to form. They do not shout. They do not claim certainty. They whisper possibilities. One of those whispers suggests that space is not continuous, that the smoothness you experience is an illusion born of scale. Beneath it, space may be composed of discrete units, much like matter is composed of atoms. This idea feels strange because we are accustomed to thinking of space as infinitely divisible. You can always imagine cutting a distance in half, then half again without end. Mathematics allows it, easily. Nature may not. Some theories propose that there's a smallest unit of area or volume below which space cannot be subdivided. Not because it vanishes, but because it comes in indivisible pieces. Geometry becomes granular. In these views, space is not a fabric but a mosaic. Each piece connects to others in specific ways, forming networks rather than surfaces. Distance is no longer fundamental. It emerges from how many connections separate one region from another. This is a profound shift in perspective. Instead of particles moving through space, space itself becomes something that emerges from relationships between more basic elements. Location is no longer primary. Connectivity is. Other theories whisper a different picture. They suggest that the fundamental constituents of reality are not points or grains, but extended objects, tiny vibrating entities whose different modes of vibration correspond to different particles. In this view, what we perceive as particles are simply resonances of something deeper. Space, then, is not made of points, but of interactions between these extended structures. Dimensions themselves become flexible. Extra dimensions may exist, not large enough to traverse, but folded so tightly that they influence physics without ever being directly observed. Geometry gains layers beyond perception. These ideas are not fantasies. They are mathematical consequences of trying to make gravity and quantum mechanics speak the same language. Both demand consistency. Both demand the absence of infinities. When forced to coexist, they hint at deeper frameworks where familiar concepts dissolve. Another whisper suggests that time itself is not fundamental, that the equations describing the deepest layers of reality contain no time variable at all. Change exists, but not progression. Events relate, but do not unfold. Time, in this picture, emerges only when systems become complex enough to track sequences, entropy, and memory. Below that threshold, there is no ticking clock, only structure. If this is true, then spacetime as a whole is not the foundation of reality, but a large-scale approximation. A useful story told by the universe when viewed from far enough away. These whispers are difficult to hear because they do not translate easily into images. They resist visualization. They exist primarily as relationships between symbols, constraints between equations. And yet, they are guided by something solid. They must reproduce everything we already know. Any viable theory must reduce to quantum mechanics at small energies. It must reduce to general relativity at large scales. It must explain why space feels smooth, why time flows forward, why particles behave the way they do. This requirement is incredibly strict. Most ideas fail quietly, collapsing under their own contradictions. Only a few remain mathematically consistent enough to be taken seriously. Even those remain unconfirmed, but consistency itself becomes a kind of evidence. When independent lines of reasoning converge on similar structures, discreteness, emergence, relational geometry, it suggests that something real may be hiding beneath, not proven, not observed, but hinted at. This is the strange beauty of theoretical physics at its limits. It is not about prediction alone. It is about coherence, about finding frameworks where everything fits without tearing itself apart. The universe, whatever it is at its core, does not tolerate contradiction, so mathematicians and physicists listen carefully to where contradictions disappear. Those places are rare, they are quiet, they are delicate, and they may be pointing in the right direction. There is humility in this approach, no claim of final truth, no dramatic revelation, just careful exploration of what could be, constrained by what must be. In this way, mathematics becomes less a tool for domination and more a form of listening. Listening to the universe's internal logic. Listening to what is allowed and what is forbidden. Listening to the echoes of a structure too deep to be seen. As you rest here, consider how different this is from the way knowledge usually feels. Most of the time, learning feels additive. You gather facts, you refine details, you sharpen images. Here, learning feels subtractive. You remove assumptions, you let go of familiar concepts, you accept that some questions dissolve rather than resolve. And yet, something remains. A sense that beneath the silence, there is order. Not the kind of order that yields easily to observation, but the kind that holds reality together, regardless of whether it is seen. Theories whisper because they cannot yet speak loudly. They wait for confirmation that may never come directly. They remain provisional, fragile, open to revision, but they also provide comfort. They tell us that the universe is not arbitrary, that its deepest layers are constrained, structured, and intelligible in principle, even if not in practice. They tell us that the limits we encounter are not dead ends, but transitions from one kind of understanding to another. And perhaps that is enough, because not all understanding needs to be complete to be meaningful. Sometimes it is enough to know that something lies beyond, structured but inaccessible, shaping everything we experience without ever appearing itself. As this part of the journey settles, one final thought lingers gently in the background. If reality at its deepest level is built from relationships rather than things, what does that say about our place within it? Part 15. Accepting the quiet unknown. At the Planck Wall, physics does not fail loudly. It pauses. The universe invites humility instead of answers. And in that pause, there's a strange comfort, proof that mystery is not a flaw in knowledge, but part of its design. For a long time, human curiosity moved with momentum. Each generation believed it stood near the end of the map. Another discovery, another. Refinement, and the picture would be complete. The universe felt like a puzzle with a final piece waiting patiently to be placed. The Planck Wall changes that feeling, not by denying us progress, but by reframing what progress means. Here, at the smallest meaningful scales, the universe does not offer a dramatic confrontation. There is no final revelation, no catastrophic breakdown of law. There is only a gentle refusal to be reduced further. A quiet suggestion that not everything must resolve into sharper clarity to be understood. Physics does not crash into nonsense. It simply reaches a point where its familiar questions no longer apply. And that distinction matters. Failure implies error, collapse, inconsistency. The Planck boundary offers none of these. The equations remain elegant, the principles remain coherent. What changes is not reality, but our relationship to it. We are asked to stop pushing and start listening. This is difficult for a species trained to solve, to dissect, to penetrate. We are accustomed to believing that deeper always means better, smaller always means truer. That reduction is synonymous with understanding. But the universe, here, suggests a different wisdom. It suggests that understanding can also mean knowing where not to press. The quiet unknown beyond the Planck Wall is not empty. It is not ignorance masquerading as profundity. It is structured, constrained, purposeful. It exists as a consequence of consistency, a way for reality to remain stable without surrendering itself to paradox. Infinite sharpness would destroy coherence. Infinite information density would collapse spacetime. Infinite precision would erase causality. By refusing these extremes, the universe protects its own integrity. In doing so, it protects ours as well. There is a temptation to see limits as disappointments, to mourn the fact that we may never directly observe the deepest layer of existence. But this perspective misses something important. Limits give shape. Without boundaries, there is no form, no rhythm, no place for complexity to settle. A universe with no limits would not be infinitely knowable, it would be infinitely unstable. The Planck Wall is not a denial of knowledge. It is a condition for meaningful knowledge to exist at all. This realization invites a quieter posture toward the cosmos. Instead of imagining ourselves as conquerors of mystery, we begin to see ourselves as participants within it. not outside observers peering in, but inhabitants shaped by the same rules we seek to understand. The unknown is no longer an adversary. It becomes a companion, and companions do not need to be defeated to be valued. At human scales, mystery already plays this role. You do not need to understand every neural impulse to feel joy. You do not need to know every molecular interaction to breathe calmly. Meaning does not require total explanation. It requires coherence, continuity, and trust. The universe offers the same bargain. It gives us laws that work, patterns that repeat, predictions that hold. It gives us enough clarity to build, to explore, to dream. And beyond that, it leaves space, quiet space, for wonder. This space is not a gap to be filled later. It may be permanent, and permanence does not diminish it. It dignifies it. The Planck Wall teaches us that mystery is not a temporary inconvenience in the march of science. It is woven into the structure of reality, and that can be comforting, because it means there will always be something larger than our understanding, something that humbles without threatening, something that reminds us we are part of a universe that does not revolve around explanation alone. It also means that curiosity does not end here. Curiosity simply changes tone. Instead of asking, "What is smaller?" we ask, "What is allowed?" Instead of, "What is it made of?" we ask, "What relationships must hold?" Instead of, "How do we see it?" we ask, "How does it shape what we can see?" These are quieter questions. They do not demand spectacle. They invite patience. And patience, in this context, is not resignation. It is respect. As you rest now, notice how this feels in your body, the relief of not needing to reach the end, the calm of knowing that understanding does not require completion, the softness that comes from allowing some things to remain open. The universe is not unfinished because we cannot fully measure it. It is finished in its own way, complete enough to sustain itself, generous enough to sustain us. Physics, at its deepest edge, models this attitude beautifully. It does not invent answers where evidence cannot go. It does not force certainty out of silence. It acknowledges the boundary and works outward from it, carefully, honestly. That honesty is one of science's quiet virtues, and it mirrors something deeply human. In life, too, there are boundaries beyond which explanation fails. Love cannot be fully reduced. Consciousness cannot yet be fully mapped. Meaning cannot be entirely quantified. These are not weaknesses of human thought. They are signs that reality contains layers where presence matters more than precision. The Planck Wall is the universe expressing that same principle. It is saying, here is where structure ends, but not significance. Here is where measurement stops, but not existence. Here is where knowing becomes a different kind of knowing, and that kind of knowing does not rush. It listens. It observes patterns rather than details. It values consistency over completeness. It is the kind of knowing that lets you sleep. As this journey comes to rest, there is no final answer to deliver, no hidden mechanism to reveal, no curtain to pull back. There is only a gentle landing. You are part of a universe that allows both clarity and mystery. It permits understanding without exhaustion. That does not require you to see everything to belong. The smallest scales may remain unreachable. The deepest layer may remain unnamed. And still the cosmos unfolds reliably around you, moment by moment, breath by breath. In that reliability, there is trust. In that trust, there is peace. So as you let your thoughts slow and your body soften, remember this quiet truth. Physics does not end at the Planck Wall. It becomes still. And in that stillness, the universe offers not an answer, but an invitation to rest inside the mystery, knowing that not knowing is sometimes the most honest form of understanding. And that is enough. As this quiet journey comes to rest, nothing has been solved, and yet nothing feels unfinished. We followed physics all the way to its gentlest refusal. We watched measurement lose its grip, space lose its smoothness, time lose its rhythm. We listened as light fell silent, as observation became too heavy, as the universe drew a boundary not of ignorance, but of coherence. At the Planck Wall, we didn't find chaos. We found restraint. A universe that knows how much structure it can carry. A reality that refuses infinities not through violence, but through balance. a cosmos that allows mystery to exist so that everything else may endure. There is something deeply calming in that, because it means the unknown is not a threat, it is a companion. The same boundary that hides the smallest scales also shelters the largest patterns, the stars, the galaxies, the quiet stability that allows you to lie here now, breathing gently, supported by laws that hold without demanding to be fully understood. You don't need to reach the Planck scale to be part of this story. You are already woven into it. Every atom in your body obeys these limits. Every second of rest exists because the universe knows when to stop dividing itself. And perhaps that is the final comfort physics offers us. That knowledge does not require total access. That wonder does not require resolution. That it is enough sometimes to approach the edge and rest there. Thank you for sharing this stillness with me. Wherever you are, whatever time it is for you, may the vastness feel gentle tonight and the mystery feel kind. Sleep softly.